Hey, hello there. So tonight I want to talk about this question, 689, maximum sum of three non-overlapping subarrays. We have an input array of positive integers, and we want to find the three non-overlapping subarrays within this input array. And if we add all the numbers from those three subarrays, they should be the maximum possible. And there is one thing that these three subarrays are in common. They all have size k, consecutive k elements in this subarrays. The k is also input to the problem. We want to return the list of indices for their starting positions. If there are multiple answers, we should return the lexicographically smallest one. So we want them to be as left as possible. If we have tied total sum for the elements, we wanted the one that towards the left as most as possible. So example, we have 1, 2, 1, 2, 6, 7, 5, 1. The subarray are of size 2. So if we look at the starting index as 0, that window, that subarray is 1 and 2, so the total is 3. If you look at the index 3, the subarray are 6 and 2, the total is 8. If we look at the index 5, the subarray contains 7 and 5, the total is 12. So 12 plus 8 plus 3, we get a 23. So that's the maximum. And there are multiple. There are another possibilities, which is 1, 3, and 5. Basically, just shifting the first subarray towards right. 1, 2, and 2, 1. They sum to be the same thing. But for this one, the lexicographically order it is larger because 1 is larger than 0. So visually it will be if we have physical arrays there, visually it will be more towards the right. So that's that's why we wanted the 0, 3, 5 here. So some guarantee here. The length is going to be within this range. The numbers here are, I think it's 8. I don't remember. 8 bits integer, and and here the k will be between 1 and 4 nums length divided by 3. That's just saying that we have to have at least one possibility for k subarrays in this array. If k is larger than this number, then there is no way we can put k consecutive non-overlapping arrays in the array. So that's some guarantee. So when you read through this question, there is really nothing special about 3 in here. There's nothing about 3 that really changes how you should think about this question. And actually, you should expect that this 3 will be maybe upgraded to 4 to be a more complex question, or downgraded to be 1 and 2 to begin with. But the end goal is to have a more generic solution that supports an arbitrary number of non-overlapping subarrays. So if you have a solution that's really doing a lot of special handling of 3 cases, then it will be a lot difficult for you to solve the follow-ups if the generic one is coming afterwards. So instead of directly thinking about 3 non-overlapping subarrays, we're just going to be thinking about this as M, and the simplest case for this question would be 1 non-overlapping subarrays. So how do we solve that? So we basically run a window where the window is basically the subarrays of size 2 from the leftmost location starting position, and just run it, slide it towards right. We're gonna shift it by 1 towards right each time. The initial one, it has the sum of 3 and the initial location index to be 0. In the next iteration, we'll move it towards right by 1. The new total is still 3, so because it's the tie, so we just keep track of the first appearance, because that will result to be lexicographically smaller. Another iteration doesn't change anything. One more iteration. The subarray now sum up to 8. 8 is larger than 3, so we update this maximum and also update the index. That becomes 3. Another iteration, we get 13. You change 8 to 13 and update the index to 4. Another iteration, we get 12. Since that 12 is now smaller than the previous maximum, we don't do any updates. One last iteration, so we reach the end of the input array. We tried all the possible size 2 subarrays. Of course, it's non-overlapping with 0 other subarrays. And by running through the window, we get the maximum for the 1 non-overlapping subarrays of size 2. The sum will be 13 and its index will be 4. So we run one window, we can solve the 1 non-overlapping subarray question. So can we just run 2 windows together to solve the 2 non-overlapping subarray question? Yes, yes, that's what we're gonna do. So initially we're gonna have, because they are non-overlapping, the best case we can do in the very beginning we're just gonna have them side by side, and we're gonna change these 2 variables to be index of 1, index of 2, which maximum of 1 and maximum of 2. This second line here is going to be the maximum of 2 non-overlapping subarrays. It's not the maximum of the second, but the both add together. So initially, this is in the initial case, it's 3 and 0. This will be 3 plus 3, and the index will be a tuple of 0 and 2. So that's the initial state. Then in the next iteration, we're just going to move this towards right simultaneously by 1 position. The first window will become 3. This first subarray will become 3. So then we only look at the maximum of 1. All we can do is compare this old 3 with this new subarray sum. It will be similar to the 1 window case. We couldn't update that in this case. But for the second subarray, it becomes interesting. The total for that subarray is now 8. And what do we compare that with? Is the 8 plus the current maximum of 1. Because there's this non-overlapping guarantee, we can always just add 8 to for the maximum of 1 there in the same iteration, which could be recently updated. Can be updated to 4 if we have 2 here, and 8 plus 3 will be 11, and because 11 is larger than the previous maximum, 6. We can update the maximum of 2 to be maximum sum of 2 non-overlapping subarrays at this given time to be 11, and the location will be updated to 0 and 3. 3 is the starting location for this subarray that sum up to 8. The second subarray that sum up to 8, 3. That's the picture here you have. In the next iteration, we're gonna shift the 2 window towards right by 1, 2 subarrays. I use window and subarrays interchangeably because they are pretty much the same in this context. The first subarray is still 3. We still can't update the first line, but the second line, this subarray becomes 13, and 13 plus 3 is larger than 13 plus 3 is larger than the previous maximum 11, and so that we can actually do the update, change the starting index for the second window, second subarray to 4. So the 0 and 4, those 2 subarrays, the new total will become 16. I'm just gonna run this through one more time. one last time actually. The first subarray becomes 8 total there, so we update this to be 8, and the index will be 3. And the second subarray here, the sum for that running subarray here will be, second running subarray will be 12. And when we consider whether we should update this maximum of 2, we add 12 with this 8, with the new maximum of 1. Because the no non-overlapping guarantee, we can always, if we process this max of 1, max of 2 in the sequence, we can always use this 12 to add the max. This we don't care about what's actually in here. All we care is the maximum of 1, and because non-overlapping, we can always use that to try to construct a bigger sum. So 12 plus 8, which is 20. That's the new maximum. It's greater than 16. And to update the indices, it's now 3 and 5. Yeah, so that's pretty much it. The two non-overlapping subarray solution is basically just maintaining 2 lines here. And you can imagine if we are actually working on the 3 non-overlapping case, we'll just have 3 windows here. So it will be 3, 8, and 12. The starting indices for them is 1 for the current subarray, sliding running subarray. It's 1, 3, and 5. Their distance, their gap is the size 2 here. The maximum for the first will be 3. The index will be 0. That's this one here. The maximum of 2 will be 11, which is 3 plus 8, and the index is 0 and 3 for the 8. The maximum of 3, and the location indices of the 3 will be 11 plus 12, 23, 0, 3, and 5. And that is exactly this input example, sample example, 0, 3, 5. So just by looking at this, if we have m windows, we're just going to have m line here. Each line is memorizing the maximum sum of the first m windows, and their indices for the m windows. So we're just going to update that. The update rule is basically max of I is going to be the maximum between the previous maximum of I and the maximum of I minus 1. Let me use a bracket to indicate this as indices, plus the current window, current subarray, I. So that's the update rule. And for the indices, we just grab the indices associated with the max of I minus 1, and just append the starting location for the current subarray I, and we can update the indices. So that's pretty much the strategy. It's going to be sliding m different windows all together, and they are side by side. The update is happening by updating the sum of the first one, sum of the first 2, sum of the first 3, maximum sum of the first 3, and so on and so forth. So we can do this update in a for loop instead of different logic, hand-coded, hard-coded logics. We can just use a looping construct to do that. So that's pretty much the analysis. Then it's the actual coding now. Sorry, my voice sounds bad because I'm coughing a little bit today early on, and but I guess you don't care. So we're gonna populate something like the window sum, which before that, the first thing to do is to make the question to be the full upper version. M, which is the number of windows that we want, number of non-overlapping windows. So what we do is first we instead of calculating this sum of k elements and all the time, whenever we shift one, we need to calculate a new sum of the subarrays. We basically do one pass and generate all this in one go, and later on we can just grab those instead of doing some extra calculation, redundant calculation. We're gonna call this window sums, and we just grab the sum by the first position for that subarray as the index. So in the beginning, it's sum of the numbers upon until the first k, and then I'm just going to do one loop. This is make sure that we have one last window that of size k. So it's instead of the last index for that would be length of nums plus 1 exclusive, decrement by 1, so that's why we need a plus 1, and we decrement by k with minus k because the window size is of k, so that's the range here. What we append is to grab the previous window, a previous subarray sum, and just discard the previous leftmost element and add in the new element. So that's the nums I minus 1 plus nums I plus k minus 1. So that's the updates. Throw out the leftmost, the previous leftmost, and add the new rightmost. And so that we can just, whenever we want this 3, 8, 12 thing, we can just call the window sum with the index number, so we don't have to recalculate every time. Then we initializing a data structure to store this line by line thing. It's gonna be we can access that by the number of subarrays we're considering. So it's a hash map with keys being the index, being the number of subarrays we're considering. The value is going to be two things: a tuple or an array of two things, which is the maximum sum of the candidate list of indices. So we're gonna have that. What are we gonna call it? Max sums. It's gonna be default dict. The default value for those is gonna be 0 and empty list. After that, we're just gonna slide the M windows simultaneously. So we got the iterator, which is gonna be the starting location for the very first window. So I'm just gonna call it S, meaning the starting location for the first sliding subarray. So the range is going to be from 0, which is the first location here, towards, it will be similar here, it's just that the k will be multiplied by m windows. Just going to copy and multiply this by m, the number of windows we're considering. Then we're just going to loop through this thing one by one. we will grab the subarray sum. You know what? I'm already calling this window, so I'm just gonna call this window sum. We're gonna use an index. So the first index is gonna be S. The first Windows starting location will be S. That's why we call this S. But for the eyes window, it will be, for the second window, it will be this S plus the window size K. So since that we're working with arbitrary number, we can just use a variable to do that, to keep track of that. So it's S plus I minus 1 multiplied by the window size K. So that's the starting position for the eyes subarray, running subarray. And we grab the sum instead of actually calculating on the fly. Actually, calculating on the fly is also okay, but I think this use a little bit extra space to speed up things. Potentially speed up things is better. Then it's just using this formula to do the updates. Grab so this window sum here will be the corresponding to the current subarray I, this thing here, and we want to grab the maximum of I minus 1. So it's I minus 1, and the max is the first item in that, so it's 0. Yeah. If it's greater than the max of I, which is using this key now, the first element, then we just override this maximum with the new maximum. And we update the candidate indices list, which will be the indices of m minus 1, the maximum of the maximum for a candidate for the m minus 1, I minus 1, I'm sorry, and concatenating this L location. So that's the updates for the windows. So in the end, we're just going to return the very last line and return the candidate indices list. So it's n and 1. So yeah, so this is the code. Let me try run through some examples. Missing one required position argument m. Oh, okay. Let me set a default here, which is 3. What the question originally is. And say submit. So yeah, it's working. So let's look at the code and do a little bit of analysis about the time and space. So this subarray sums is pre-calculated. The size is it's obvious. The length minus k plus 1. So it's order of n. If we have n numbers, so that's space and the time for generating this portion. Then looking at this data structure here, the hash map. The keys are the m windows. The space requirement here is dominated by the candidate list. So the first window, it will have for the first subarray, it would just have one index number. But for the very last one, the m, it will be m element here, m index there. So it's 1 plus 2 plus and go all the way up to m windows. M subarrays, I'm sorry, they're interchangeable. I guess you should be okay with understanding. So it's m squared. That's the space for this data structure, for this hash map. It's predominated by the number of index that we want to keep track of. So that's for the hash map here. For this looping condition here, it's the outer loop is order of n. You know, we're looping through all the lengths minus some constant smaller things. If the k and m are relatively small, the array is big. This is pretty much just order of n. The second loop, inner loop, is order of m. So the time for this is n multiplied by n. N is the array size, m is the number of windows, number of subarrays. For space, there's nothing here. So this space is the m squared plus n. And if we want to optimize for space a little bit, we can choose to not do this, but instead we can put one element in the hash map to be the window sum, to be the running subarray sum. And instead of doing this calculation just in a one-off fashion, here for each of those windows, we're gonna, instead of grabbing that from the pre-calculated result, we can just do the subtract and addition here with this index to be some kind of multiple of k and offsetted by the s. So that can remove the requirement for populating this. So dropping the time order of n and the space order of n. So the space will be strictly m squared, but I think that will be a little bit more tricky to write in interview time. You have to deal with this s, and you know, this will be complicated. The number will have a multiple of another loop, another thing here. The I here, another Sam. If you decide to do that here, it will be s plus. I don't even want to. I don't even want to talk about that formula, but it's easy to get it wrong. So. Anyway, this is the question. It's a generic version solution, so it supports arbitrary m. If you look at the analysis, it's really not anything different from 1 or 2. Yeah, all the thing here is just this relationship, and that's pretty much it. All right, so that's the question for today. Yeah, bye for now.